The dynamics of leading power factor. Good day, everyone. Welcome to this advanced session on power system dynamics. Today, we are diving deep into a topic often overlooked in basic electrical engineering, the dynamics of leading power factor in AC systems. This condition is crucial for managing grid stability, especially in modern utility and industrial environments. We'll explore the causes, the critical risks it poses, and the strategic tools used to mitigate its effects. Core fundamentals. We'll begin by establishing the fundamental physics that define this phenomenon. Understanding the core shift in the current-voltage relationship is the foundation for analyzing all subsequent system behavior. Defining the leading edge. The simplest definition of a leading power factor is the phase relationship where the current precedes voltage. As you can see on the waveform, the current reaches its peak before the voltage does. This condition is the direct result of capacitive dominance, meaning the overall circuit impedance is dominated by capacitive reactance, X_C. As the formula shows, capacitive reactance is inversely proportional to frequency and capacitance. Essentially, a leading power factor is the inverse scenario of the more common lagging power factor caused by motors and induction equipment. What causes leading PF? A net capacitive load can arise from several sources. First, and most common, are capacitor banks. These are intentionally installed for lagging power factor correction, but if they remain connected during periods of very light inductive load, say, overnight, they can overcorrect and create a system-wide leading PF. Second, underground cables inherently possess high shunt capacitance due to the close proximity of conductors separated by dielectric insulation. The longer the cable, the greater the capacitance. Finally, certain electronic loads, such as large, modern uninterruptible power supply systems or variable frequency drives, especially when lightly loaded, contain input filters that present a net capacitive load to the grid. Reactive power and phasing. The key difference in leading PF is its role in reactive power flow. Capacitive loads perform reactive generation, they actively supply reactive power, Q, to the system, rather than consuming it. This is why leading power factor is sometimes recorded as generating negative kVAR. Visually, on a phasor diagram, the current vector is rotated ahead of the voltage vector. The phase angle, phi, falls between 0 and -90 degrees, confirming the capacitive nature of the load. Voltage magnification. One of the most dangerous side effects of a leading power factor, especially on long transmission lines, is the Ferranti effect, or voltage magnification. When the generated capacitive reactive power travels down a long line, it interacts with the line's inherent inductance. This interaction causes a buildup of voltage, making the receiving end voltage rise significantly higher than the voltage at the sending end. This voltage rise can stress insulation, compromise equipment, and ultimately lead to grid instability. System efficiency impact. While leading PF is often seen as better than lagging PF, it still represents an inefficient use of the grid. The general rule still applies: apparent power, kVA, will exceed real power, kW. The high phase angle means that the current carrying the real power is only a fraction of the total current flowing. This excess current increases losses in conductors and transformers, demanding larger, more expensive equipment even though the useful power output has not changed. Generator instability. Perhaps the most critical issue is the threat to power generation equipment. Operating a synchronous generator into a leading power factor creates a severe demagnetizing effect in the machine's armature. This requires the generator's automatic voltage regulator, AVR, to aggressively reduce the field excitation current. If the excitation is reduced too far, the magnetic coupling that holds the generator in sync with the grid weakens, causing the generator to lose stability, overheat, and potentially experience a mechanical failure known as slipping poles. This is why generators have strict operational limits on how far they can operate into the leading region. Correction dynamics. The goal of power factor correction is to offset the system's primary reactive load. Capacitor banks are the tool used to neutralize lagging PF. Automated controllers are the control, carefully switching capacitor steps in or out based on real-time load measurements. However, the constant risk is overcorrection, which pushes the system into an unstable leading state. Mitigation strategy. When a system becomes overcapacitive and develops a large leading PF, the solution is straightforward. We must introduce an opposing reactive component, which means adding inductive loads. Utilities and large substations use specialized equipment called shunt reactors, essentially massive air core or iron core inductors, to absorb the excess capacitive AVR. By connecting these reactors, they stabilize the system, mitigate the Ferranti effect, and pull the overall power factor back towards unity. Quote. As we conclude the technical discussion, remember this core principle of electrical engineering: management of reactive power, whether leading or lagging, is the keystone of grid stability. Achieving near-unity power factor is not just about efficiency, it's about the safety and resilience of the entire power system. Q&A. Thank you for your attention. I'm now open to any questions you may have about leading power factor, the Ferranti effect, or generator operational limits. If you have follow-up questions later, please feel free to reach out.